This lesson is going to be on discrete probability distributions. So our objectives here that you can distinguish between discrete and continuous random variables, and we've done this a little bit earlier. We just talked about discrete and continuous data. Identify discrete probability distributions, and we're going to construct probability histograms and interpret the mean of a discrete random variable, and interpret the mean of a discrete random variable as an expected value. We may actually not do that one. And we're going to compute the variance and standard deviation of the discrete random variable. Okay, so what is a random variable? A numerical variable whose value depends on the outcome of a chance experiment is called a random variable. So it associates a numerical value with each outcome of a chance experiment. So it's discrete if the values are isolated points, generally something that we can count. So it may look like this. It's sort of a picture. We're able to physically count the numbers. It's continuous if the values include an interval of some numbers, usually something we measure, weight, time, length, things of that nature. So graphically, values can fall within a range of values like this. Okay, so let's determine whether the random variable is discrete or continuous, and in each case let's state some possible values of the random variable. Okay, so A, the number of defective keys on a keyboard. What do you think? If it's something, so think in your head, it's something that we can physically count, we're going to make it discrete. If it's more of a measure of something, it can be continuous. So number of defective keys on a keyboard, this is certainly discrete. I'm just going to use a D for discrete. And some examples here: 0, 1, 2. Sometimes I'll put an X equals. Okay, so those are some possible values we could have. How about the number of pages in your textbook? Discrete again, right? Again, very similar. I can count my pages very similarly. 1, 2, and so on. The lifetime of a compact fluorescent light bulb. So again, this is a time that we're measuring. We're not counting it, right? So this is going to be continuous, and we could have, I'm not sure if it's measured in days or whatever, but let's say, or probably measured in hours. So it could be 500 hours, 600 hours and 30 minutes, etc. The amount of rainfall Murfreesboro received in the month of May. Again, this is the amount of rainfall, something we're measuring, so this is continuous. What are some examples here? Maybe we're going to be in inches, so we could have received 3.2 inches. So again, we could say X equals on these. X equals 3.2, X equals 4, etc. The number of DUIs cited by MTSU campus police. Discrete, right? Because I can count the number of DUIs given by MTSU campus police. Again, the number of DUIs could be 0, 1, 2, and so on. You know, I don't have like 2.3 DUIs or something like that. So generally, our discrete data is going to be nice countable numbers. Not every time, but generally that's what we're going to be looking at. The square footage of a house. We're measuring, right? So we're measuring the length. And just because our rounding or our measuring tools have to round does not make it discrete. So again, this is continuous. Some values here. X could be 2,200 square feet. X could be 3,400 square feet, and so on. The wait time in a line at Wendy's. Again, another continuous. X could be 5 minutes. Let's say we're in minutes. X could be 3.5 minutes, 3.5 minutes. Now, what if we said the number in line at Wendy's, the number of people that are actually waiting for food? That would be discrete. So hopefully these examples clear up any confusion you've had earlier on discrete versus continuous. So probability distributions. So the distribution provides the possible values of the random variable. It's going to give them all. So it can be in the form of a table, a graph, or other formula. And here we're pretty much going to be looking at it in the form of a table, and then I may have you graph these. So for example, suppose you flip a coin 2 times and record the number of heads. The following would be a probability distribution. Just think of all the possible values. So x is my random variable, the number of heads. Again here, x is the number of heads. So again, I flip a coin 2 times, so what could possibly happen? I could get 0 heads, right? I could just get tail, tail. That's that outcome. Or I could get 1 head. I could get head, tail, or tail, head. Or I could get 2 heads, head, head. So, if I were to list these all out, I could get, I could get tail, tail. I could get head, tail, or tail, head, or head, head. This is called the sample space of the experiment. It's the list of all the possible outcomes. This is really what we're looking for here. I'm just kind of showing you how we're getting this. So this is, for counting the number of heads, how many heads do we have in this first one? I've got 0 heads. How about in the second one? I've got 1 head. How about the second one? I've got 1 head. And this one I've got 2. So my possible values are 0, 1, and 2. Okay? Now, here are the probabilities. If you're not comfortable, I'm pretty much going to give you probabilities here. How do we figure out probabilities? The number of successful outcomes over the number of total. So if we wanted to compute these, 0 heads, we have 1 successful outcome over a total of 4, so that's why I get 0.25. 1 head, we have 2 successful outcomes over a total of 4, so 2 fourths is 0.5. And then 2 heads, again, I've got 1 successful outcome, 2 head, head, over a total of 4. In this lesson, I'm pretty much going to be giving you these, unless it's super basic, like the probability of getting a question right on true, false, right? Okay, so here is the probability distribution. Again, here are my associated probabilities. So just an interpretation here, P of 0 equals 0.25. So this means the probability of getting 1 head is 0.25. This can also be written as the probability of, and sometimes we'll put x equals 0, is 0.25. Both notations are used. This one here is sort of the more formal notation, but I think our book uses this one a little bit more often. So what's the probability of getting at least 1 head? So we need to get comfortable at what this sort of language means. At least, at most, things like that. So at least 1 means what? It means the probability of 1 or what? 2. At least 1 means 1 or more. So what do you think we're going to do here? We're just going to add them up. You're going to add up 0.5 plus 0.25 to get what? 0.75. So another way to do at least, and this may be confusing at first, is notice the only one that's left is this one right here. We can do 1 minus the probability that we get this one, but we're not going to worry about that right now. We'll look at that later with binomial. Okay, requirements. So we have 2 requirements. The sum of the probabilities must be 1, or very close. Just due to rounding, we may get 0.999. And then each probability has to be greater than 0, or equal to 0, or less than or equal to 1. Right? So I can't have a probability of negative 0.3 or 7. It's always going to be a number between 0 and 1 inclusive. 0 means it can't happen, 1 means it's absolutely certain to happen. So note in our previous example, we had 0.25, 0.50, 0.25. The sum equals 1, and each of these are in between 0 and 1. So that was a probability distribution. So example 2, determine whether the distribution is discrete, is a discrete probability distribution. Okay. If not, state why. So pause the video here, see if you can look at these 3 separate distributions and see if you can figure out, I'll give you a hint, 1 of them is a distribution and 2 of them are not. Okay, welcome back. I know you paused that video. So let's look at the first one. So I can glance here, I notice that each of these values and my probabilities are between 0 and 1, right? So that's condition satisfied. But do they sum to 1? Is the sum 1? So 0.2 plus 0.3 is 0.5 plus 0.5 is 1. Uh-oh. 1.1, 1.3. So my sum of the probabilities is 1.3. And that violates the sigma means sum. And that violates one of my properties, right? So this one is not. And here's the reason why. The sum is 1.3. The sum needs to be 1. We're super close. 1.001, 0.99, just due to some rounding errors, maybe. Okay, how about the second one? I should have labeled these maybe A, B, and C. How about B? So B is going to be what? What's the red flag right here? Here we go. We don't have a negative probability, so this one is not. Because the probability here is not between 0 and 1. And how about the third one? So we look, all these are between 0 and 1 inclusive, and 0.3 plus 0.1 is 0.4, 0.5, 0.6, 0.7, so 1. So yes, it is. Because the sum is 1, and each of these are between 0 and 1. Okay, let's graph these. So if I had this, and I want you to draw a histogram of the distribution, what would it look like? Okay, so let's just put our values here. For discrete, we can just do 0, 1, 2. And look at our highest value is 0.5, so we'll call that 0.5. That's 0.5, and right in the middle is 0.25. Okay, so we're going to do 0 is at 0.25, so there's our 0.25. 1 is at 0.5, so just go up to 1. And 2 is back down to 0.25. There we go. There is our graph. And this is what it would look like similarly on the TI. Now let me show you how to graph this on the TI. Okay, so what we're going to do, we're going to go to Stat, Edit, we're going to put our list in. So let's clear these out, my L1 and L2. And so I'm going to put X in the L1 column, so 0, 1, 2. And then in the L2 column, I'll put my probabilities, 0.25, 0.5, 0.25. Let's go to second y equals, the stat plot. Let's turn it on. So we have the histogram selected, so make sure you go down and select histogram, and then make sure your list is L1, and your frequency is going to be L2 now. Let's do a zoom 9. That doesn't look very good, does it? I mean, the calculator does its best to create the optimum number of bins. The problem is we only have 3 bins. I mean, 3 numbers here, but it works better if you've got more. So I have to go in and manually change that. We may have done that a little bit in an earlier lesson where we talked about histograms, but now we kind of need to because this is a discrete. We have discrete numbers here. So I want my X scaling here to actually be 1. Okay. And X max, I can bump that back down to 3 if I want. And let's go ahead and graph this. And just press graph. There we go. You can kind of see I've got a graph very similar to that. We're just basically looking for the general shape of the graphs. You may need to go in and adjust the Y min or Y max if you feel you need to. You certainly can. So Y max probably doesn't need to be quite this high. We can see our max is 0.5. So I'll make it a little bit bigger than that. And don't need Y min to be at negative 0.22, maybe just negative 0.1, just so I can see the axis and graph. I'm not that picky on that. We're just looking for the general shape. And again, notice if I trace, I'm here at 0, and it tells me it's 0.25. I'm here at 1, and it's at 0.5, and I scroll over again to 2, and it's at 0.25. So we get a nice visual of the distribution. Okay, example 4. Let X denote the number of broken eggs in a randomly selected carton of 1 dozen eggs. Suppose the probability distribution of x is as follows. And then we got 0, 1, 2, 3, 4, and then p of x is 0.65, 0.20, 0.10, 0.04, and 0.01. So how would you interpret p of x, the probability that x equals 1 equals 0.2? What does that mean? So pause the video here and see if you can think about that rather than me just giving you the answer. And I think you can probably figure out B, C, and D as well. Okay, welcome back. So the probability that x equals 1, that's this one right here, right, is 0.20. I could have just asked you what is the probability of x equals 0.2. What is the probability of x equals 1? But I went ahead and asked this. Again, this could have also been read as probability of 1. So this means the probability that I select and I get one broken egg is 0.20. So again, the probability means this. It means that about 20% of the cartons have exactly one broken egg. Again, 20%. So 0.2 is a decimal of 20% of the cartons have exactly one broken egg. So if I had a just imagine a big sample of, picture these being cartons of eggs. These are the cartons, not the eggs. So each carton's got a bunch of these, a dozen eggs, right? I'm not going to be able to squeeze them all in there, but just imagine a dozen eggs in these cartons. Those are my eggs. Those are a dozen eggs in each one. So just imagine a bunch of these cartons of eggs, right? That 20% of these cartons, I dip in and get a carton. 20% of the cartons themselves have exactly one broken egg. Okay. Think about the next one, B. Okay, I went ahead and wrote that out for you, as that's important that you can interpret that. So calculate the probability that x is less than 1 and interpret. Okay, the probability that x is less than 1 would be what? Just the 0 right here. It's the same thing as saying the probability in this case of x being 0, which is 0.65. So that means that 65% of the cartons have no broken eggs, right? Hope I don't need to write that down. Same thing as this one, except we just changed the numbers around. So 65% of the cartons have no broken eggs. How about this next one? The probability x is less than or equal to 1. What does that mean? So this is x equals 0 and x equals 1. So we have to include both of those. Technically I guess. So x equals 0 or x equals 1. So we can just add those up. So x equals 0 plus x. We're just going to put 1 right out of room there. So what is 0 is 0.65 and 1 is 0.20. So we end up with 0.85. So again, the interpretation, 85% of the cartons have 0 or 1 broken eggs, or less than or equal to 1 broken egg. Okay, calculate probability that x is in between 1 and 3 inclusive. So again, what does this mean? This means the probability, I'm just going to put the numbers here rather than the x's, the probability of 1 plus the probability of 2 plus the probability 3. So that we have 1 broken egg, 2 broken egg, or 3 broken eggs, right? So that's going to be the sum of these numbers right here. So that's going to be 0.2 plus 0.1 plus 0.04. And this is 0.34. So in decimal, as percents, 34% of the cartons have between 1 and 3 inclusive broken eggs. So means and standard deviation. So example 5, suppose we flip a coin 3 times and record the number of heads. And the probability distribution I've given over here. Find the mean and standard deviation. Okay, so again, just sort of take these probabilities as they're given. We would have computed those in an earlier lesson. Okay, so how do we find the mean? remember the sigma is just sum, right? So we're just going to sum up x times p of x. So 0 times 0.125 plus 1 times 0.375 plus 2 times 0.375 plus 3 times 0.125. And we get 1.5. So on average, if I flip a coin 3 times, we expect about 1.5 heads to come up. Now obviously I can't get 1.5 heads. This is sort of a theoretical mean, right? So between 1 and 2 heads is what our expectation is. Now thankfully the calculator does this without us having to do that. I mean, that wasn't that bad in this problem here, right? When we had pretty small numbers, only 4 different rows here, but these can get really lengthy. So let's do this in the calculator. Again, as you would expect, put the x list in L1 and the p of x in L2. Okay. So again, put the 0, 1, 2, 3, and then put the 0.125, 0.375, 0.375, 0.125. Do the 1 var stat. You got to put L1, comma L2. Again, you have to do this. Make sure you do that. You'll get the wrong answer if you don't. And here's our mean. So our mean is 1.5. Standard deviation, it's got to be the population, so you can't possibly mess this one up, is 0.867. Or 0.9. I'll give you a rounding rule here in a second. Here it is right here. So we generally, when we round, we go one more decimal place than the number of decimal places used in the random variable. So our random variable x, before we had 0, 1, 2, 3. So we're going to go one more. So he's the nearest whole number. So we're going to go to the nearest 10th when we get our mean and standard deviation. I'll sometimes go 2 on standard deviation and 1 on the mean, but I think this book uses the one more decimal place and the number of decimal places used for the random variable. Okay, example 6. I think this is the last one. May have one more after this. The following data represent in thousands the number of 5 to 9-year-old females in the U.S. in 2000. So construct a discrete probability distribution. So again, number of 5 to 9-year-old females. So again, 5-year-old. We didn't have 1,934. This would be 1 million, right? Because these are in thousands. So technically, I've got 3 zeros at the end of this. But sometimes we do this in order to keep our numbers a little bit more manageable. So what do I need to do? How do I find the probability? I mean, very similar. This is very similar to the relative frequency distribution, right? In fact, it's exactly the same way. I've got to find the total. So find your total here. Just add them up, see what you get. You end up getting 10,025. So we just divide each one by 10,025. And we get our numbers. And probably best just go ahead and rewrite that so it's a nice one, clean looking distribution. Look familiar? This is very similar to the relative frequency that we did in an earlier lesson. Okay, part B, let's sketch a probability histogram. Okay, here's what it looks like if you were to maybe use a Minitab or something, a computer program. You could just sort of sketch that out. Let me go back to it. There's not a lot of variation here, right? I mean, so if we're gonna do it right here, 5, 6, 7, 8, 9. Again, look for your max is 0.208. So we'll call that 0.210. I usually just go a little bit above that. And there's my halfway point. And so all these are going to be really hovering. We can kind of see a general increase here. So there's our first one. This one goes up just it goes up 3 1,000ths. So I mean, it's not going to register that much for you. This one goes up 4 1,000ths, and then 8. So 5, 6, 7, 8 goes up another little bit, and then 9 another little bit. Again, it's not going up much. I mean, over 5 years, we're only going up, 15 1,000ths. So it's not going to show this going up too much. So on the TI, when we put this in, again, you're going to put an L1, you put the list in L1, put the probabilities in L2. Go back and change your X scaling to 1, because these all these here are increments of 1, right? 5, 6, 7, 8, 9. Change that to a 1, and there we go. Again, because of just the pixelation, the appears are the same for each one of these. So you may have to scroll over on some of these to see what you got. Let me do this one live for you. So I want you to get pretty good at this. So again, go over here to your stat, edit. We're going to put 5, 6, 7, 8, 9. And probabilities, 0.193. 0.2, 0.204, 0.208. I think that was right. So again, stat plot, make sure it's on. I always look at this when I'm doing these, make sure it's on. X list L1, frequency is L2. I've got my histogram. So I do a zoom 9. Zoom 9 is not going to work that well. I can only get 2 bends here. Go back to window, change that to a 1. And look at your max. I mean, you kind of glance down and see what your max is. I'm at 0.208. So again, let's make our max. Well, let's see what happens if I keep it at that. Let's see what we get when I just press graph. I can kind of see it begins to edge up a little bit, but I want a better looking graph than that. So hit window. And let's change Y max to 0.3. Then graph that. I can see it goes up a little bit better. I've got a lot of room here on the x-axis and a lot of room down here on y-min, so I'm going to change that. Let's change this to maybe negative 0.05. And then change your x max. We don't need up to 13, do we? We're just going up to 9, so let's make this maybe 11. There we go. Looks a little better. I can kind of see a steady increase if I press trace. I'm at 5, it's 0.193. At 6, it's 0.196. Can't really see much increase there, but you can definitely see it notch up a little bit there and notch up a little bit here. Again, you may find these easier to do by hand. You'll eventually want to be able to use the calculator when we start doing a lot of these. I'm going to want you to sort of describe the distributions of these when we have lots of data points. So this one here doesn't even look right, does it? It looks like this screenshot here was only plotted with L1 and not with L1, L2. Okay, so now we want to compute and interpret the mean and standard deviation of the random variable. So again, I've got a screenshot there for you to have in your notes, but we'll do this live while we're here. I'm going to stat, calc, 1var stat, but I have to do L1, comma L2. Get in the habit of doing that. And press enter. I get the same thing I got there. So there's our mean of about 7.0, and we're going one more decimal point than the number in my random variables. Standard deviation is about 1.4. And we have other values here if I ever ask for them. Have those underlined there for you.